Hello, and welcome to Main Group 24's project proposal on the Intelligent Autonomous Drone Aid Delivery System with Minimal Human Intervention. This project was conducted by myself, Ramon Ponce, Ian Blankenship, Ethan Gable, Kenneth Nguyen, and Sebastian Valenzuela. Now, the project summary. This capstone project centers on developing an AI-powered drone for humanitarian missions. This includes a drone for search and rescue reconnaissance to identify people in need, and a delivery mechanism for deploying aid in areas of disaster or conflict where ground transportation simply isn't viable. This will all be coordinated through a WinTAC home system to minimize the need for any manual or pilot involvement. The system aims to improve efficiency and emergency response by automating critical tasks and integrating AI-driven surveillance and delivery into critical situations. Now, the problem that we discovered was that a lot of the time where you might need emergency response are in areas where there are natural disasters or conflict zones or challenging terrain or adverse weather conditions. And this makes transporting aid by hand super difficult. Food, water, critical supplies, medical aid, all just barred because they're in an area where people just can't get there fast enough or in time. And this can be the difference between life and death. Humanitarian agencies traditionally rely on ground-based transportation, which can be slow, resource-intensive, and simply inaccessible if the infrastructure to do so is damaged or the environments are hostile. These delays can lead to a loss of life that is otherwise preventable if aid is more accessible and is readily available. Now, the significance with this problem is simply the fact that people can die. There are a lot of risks that humanitarian agencies take to try to deliver aid, and these risks can be mitigated with our drone. Our drone has two responsibilities: the reconnaissance aspect, which is meant for search and rescue and is equipped with an AI-driven image recognition and data analysis capability. The main objective is to identify individuals in need and collect real-time data on environmental conditions, no matter the condition, and on affected populations to optimize the delivery process flight path. The second responsibility is the delivery system. This will be responsible for transporting and deploying aid packages through a touchdown or through a flyby overpass drop to ensure adaptability across environments and conditions. With these two responsibilities, the drone should be able to quickly, efficiently, and safely deliver aid or find those in need much faster than the traditional methods used by humanitarian agencies, in a more cost-effective way.
For this project, we require a couple of things. In terms of the data collection, we want our drone to capture high-resolution images and videos of the affected area in real time, and while also processing the data using AI algorithms to identify individuals needing aid. In terms of aid delivery, we mentioned that the drone should deploy the aid via touchdown overhead pass while also having a minimum payload of 5 pounds. And the system should also support automated delivery to GPS specified locations with an air margin no more than a meter. In terms of communication and coordination, the WinTAC home-based system shall coordinate all drone systems in real time and provide the operator with mission updates. And in terms of modularity and scalability, the system should also be able to integrate additional drones for additional coverage, and the design shall support upgrading hardware and software components without impacting the already pre-existing functionalities of the system. In terms of the user interface, we want it to be something really simple. So the home-based system shall provide a graphical user interface for mission planning and monitoring. And the user interface shall also display real-time drone position, status, and mission progress on a map. And in terms of ease of deployment, we want the drone to be able to deploy in less than 5 minutes and should support a semi-autonomous operation requiring minimal user intervention during missions. For form factor, the drone shall weigh no more than 10 pounds, including the payload, to allow for easy transport setup, and the drone should be compact and foldable with a maximum dimension of a meter and a half a meter. And in terms of environmental adaptability, the drone shall be able to operate from temperatures from -10 degrees Celsius to 50 degrees Celsius and withstand wind speeds of up to 50 kilometers per hour. And the system shall function in challenging environments like fog and rain. In terms of safety, like collision avoidance, we want the drone to be equipped with sensors and software to detect and avoid obstacles within a 10-meter radius, and also let the operator know if a potential collision is detected. For the battery empowerment power management, the drone shall return to the base station when the battery levels falls between 20%, and the system shall include safeguards to prevent overheating or overcharging of batteries. And in terms of more safety, the payload safety, the delivery drone shall secure payloads during transport to prevent damage or accidental drops, and should also include fail-safe mechanisms to ensure that the payload deployment only at specified locations. And for the emergency shutdown, we would like the drone to automatically shut off the rotors if hardware or software failure is detected, and should provide the operator with an emergency stop button just in case to halt all drone operations. And for regulations compliance, the drone shall comply with all aviation safety regulations in their operating region, and also include a mechanism for geofencing to restrict operations in prohibited areas. We also have a diagram of the process in which we talk about the communication process. So the reconnaissance delivery drone should send reconnaissance data to its antenna, in which the antenna forwards the data to the WinTAC system for further data processing. And within the WinTAC system, the received data will be processed and analyzed. It involves segmented specific operations to ensure that the data's integrity is and also complete and usable. The data is also validated to determine completeness and accuracy. And we also have a loop just in case if the data is valid, the WinTAC will send a confirmation to the drone via antenna to acknowledge that the data received is valid. And if the data is invalid, the WinTAC will initiate a request for data retransmission, and the drone will respond by resending the data. And then the drone will acknowledge the receipt of commands with the communication module to ensure that the communication is reliable and coordinated with the WinTAC system.
I'd like to begin with an overview of how the subsystems are designed and implemented to work together effectively on our project. Starting with the drone's AI and navigation capabilities, we use TensorFlow or PyTorch models for object detection and image classification. These frameworks allow the drone to identify individuals independently in need and assess its surroundings using real-time video feeds and data input. To ensure stable flight and autonomous navigation, we rely on ArduPilot or PX4 autopilot systems. These systems manage the drone's stability and ensure that it follows its programmed route with minimal human intervention. Where it relates to communication between the drone and the home base, we implemented Mavlink, which is a lightweight protocol that ensures reliable data transmission, enabling the drone to send updates and receive commands efficiently and effectively. Moving on to the AI training and decision-making process. The AI models we use are trained on open source datasets, which are processed using cloud computing resources. This allows us to refine the drone's decision-making capabilities without putting too much burden on its onboard hardware. For navigation, we've implemented path planning algorithms using OpenCV and the robot operating system, which calculate efficient routes. Additionally, LiDAR integration helps the drone detect and avoid obstacles in real time, enabling it to adapt to dynamic environments. Finally, for the custom firmware, the firmware ensures that payload handling and deployment are secure and precise as they need to be in the specific use cases we are planning for. This is especially important in delivering to specific locations, as mentioned previously, without causing damage or error. Now that the subsystems are covered, I would like to take a closer look at the hardware components that bring the system to where it is. Starting with the servo motors, we are using 4 9-gram servo motors to control the drone's roll, pitch, and yaw. Their lightweight design will ensure that we have precision in maneuvering the drone without adding unnecessary weight. The electronic speed controller, or ESC for short, is critical in managing the motor's speed and power usage. It ensures that we have efficient energy consumption and maximizes the battery life for longer missions, like we've talked about. We also have the brushless motor, or the brushless A2212/6T 2200 kV motor that provides a high thrust while also similarly minimizing energy loss. This balance is crucial to enable longer flight times and to maintain performance over time. The Raspberry Pi acts as the drone's brain, essentially. The Raspberry Pi is going to process sensor inputs, run AI algorithms, and coordinate navigation. Its versatility and computational power, it makes it essential for our drone system. We also have the LiPo battery. The 7.4 volt battery was chosen for its high energy density and, with emphasis, its lightweight design. It provides power that we need for the drones to ensure longevity without putting too much burden on the hardware of the drone. We also have our GPS module. This will ensure accurate navigation and allow the drone to pinpoint its destination and stay on course throughout the mission. We have our GoPro camera, which will capture high-quality visuals and, additionally, allow the drone to operate effectively even in low visibility conditions. We have our AKK FPV video transmitter, which will ensure stable real-time visuals will be sent to the home base, with its long-range capability making it ideal for maintaining situational awareness during these important missions. The last component that I would like to discuss is the FlySky FS-I6X radio controller. This radio controller will provide a backup for manual operation, offering reliable communication just in the event that the autonomous systems encounter challenges or problems during a mission.
My name is Sebastian Valenzuela, and I'll be talking about challenges with subsystem implementation. A few of the challenges we might face are the reconnaissance capabilities of the drone. Developing an AI model that accurately identifies individuals needing aid from aerial imagery is difficult, especially in environments with poor visibility, dense foliage, or urban clutter. False positives or negatives identifying targets could also delay or misdirect aid delivery. Processing high-resolution images and videos in real time requires significant computational power, which could constrain onboard hardware. The drone and sensors might struggle in certain environmental conditions like fog and rain, reducing the effectiveness of reconnaissance. It would also be challenging to transmit large amounts of data to the home base without significant delay, particularly in remote and signal-blocking areas. Another potential challenge would be delivery capabilities of the drone. Designing a mechanism that can handle varying payload sizes and weights without affecting the drone's stability or flight performance would be difficult. Ensuring the payload is secure during transit and deployed precisely at the designated location adds to design complexity. High precision in GPS-based navigation can be difficult in areas without satellite coverage. Adapting to dynamic environments, such as moving targets or obstacles, requires robust navigation algorithms. Limited battery life would restrict the delivery range, necessitating efficient power management and lightweight designs. Balancing payload capacity with flight endurance requires an optimization problem for a balanced trade-off. Maintaining consistent communication in areas with high electromagnetic interference or physical obstructions could also be an issue. Extending the communication range without introducing significant latency or bandwidth issues requires complex signal processing and transmission technologies. Also, operating communication equipment for a long duration could quickly drain the drone's battery, which limits its use for extended missions. Moreover, the WinTAC home base. Aggregating data from multiple drones and sensors in real time while ensuring synchronization and accuracy is computationally intensive. It's essential to ensure that the system can process, analyze, and present data efficiently without overloading the hardware or software. Developing an intuitive and user-friendly graphical interface that provides all the information without overwhelming the operator also poses a challenge. Ensuring the system can accommodate additional drones or new functionalities without compromising performance or requiring major redesigns is essential for long-term usability. Finally, modularity and integration. Standardized communication protocols and integration frameworks are required to ensure seamless communication and coordination between the drones and home-based system. Compatibility issues between different hardware components and software systems could delay development. Moreover, testing in diverse conditions to validate the system's performance and reliability is resource-intensive.
So this first early prototype picture is of the body of the fixed-wing drone. At the beginning, we have the brushless motor. Attached to it is an 8-inch prop. Right here is the motor mount that's specifically designed for this brushless motor. Now these are the front plates. They're meant to both elongate the body but also move the motor away from the body. Now this is the main body. Right here are two braces here to give the body a little more stiffness. Below is the bottom plate, and these two are the side plates. Their little groove right here is to help fit the airfoil, make it nice and snug. It's also made so the angle of attack is at approximately 10 degrees, so when it's at takeoff, it will be able to generate enough lift to take off. Now back here is the tail. So right now we have just the tail piece, basically. It's not complete yet because we need to add the rudder and the elevator to the back. Now, in the middle section, which is going to be where all the electronics are housed, right at the bottom, we have the LiPo battery. Now, this is quite a large battery for this size of a drone, especially if it's going to be fixed wing because they tend to be a little more efficient. However, that means it'll give it a longer run time. Now, it has to be in the center because of weight and balance. The wings are going to be right on top, and we want the center of gravity to be close to the center of lift. Now, coming from the motor is the ESC that goes into, while you can't see it here, a simple Arduino. Now, this Arduino is just being used as a microcontroller to see how the motor and the ESC are functioning. As you can see right here, this is just a potentiometer. It's just a throttle control at the moment. Later, the Arduino will be used to actually control all the servos that control all the flight surfaces. Speaking of flight surfaces, next slide. So this is a prototype of the wing. The actual wing is going to be quite a bit larger at the end. So we have the wing spar, which is in the shape of the airfoil. It's what gives the wing its shape. Right here are all just braces, basically, like just ribs of this to like make it, give it spacing, but also like give it strength. We want to reduce weight. At the end of the day, we rather it be lifting a payload and its electronics than the wing itself. Right now we have a servo. The servo is currently, we're researching the best way to put it in order to fit the form factor of the wing, but also give us a good leverage on the aileron that it controls. Now this is the aileron. Right here are the two pieces that connect it to the wing. So the aileron will go, is supposed to go up and down controlled by the servo. Now, right now, as you can see, this is all 3D printed, same with the body. It's all printed in nylon filament, which is a strong but flexible filament. Everything is connected using M3 bolts. The final is probably going to be more slotted in than glued. We're thinking for the wings of using balsa wood. Now, the reason it's bolted right now is so we can modulate it and change it as we go without wasting too many resources. So basically, each section is we have the spar here, goes over here, another spar, and we can continue it out. Right now, this wing is probably a little short, and the bolts are going to put a lot of, they're going to have a lot of shear on them. So we're probably going to switch to carbon fiber tubes that are both stiffer, but also be able to slot into the center section better. Now, the servo is going to be controlled by the Arduino, and we have a multiple servo controller that will control all of them. So this is an example of the left wing. Now, this servo is going to control this flight surface right here with the left aileron, and the right is going to have the right aileron, of course, controlled by another servo. Those usually move opposite of each other. Now, on the back, even though we don't have it, it's going to control the elevator and the rudder. Those are going to be 2 more servos, bringing up our total to 4 servos.
The outline of the project is planned to finish all the preliminary stages by mid to late December. Then drone construction begins, and preliminary starts to UAV simulations and AI training. The drone is expected to be completed and then tested to ensure it runs correctly before the AI models are expected to be completed. Then, new tests will be conducted with the models to ensure a working product is complete without problems. After this, minor adjustments and QA checks will be done as a precautionary measure. Next slide. So, task breakdown and key milestones. This is a screenshot from Trello, but basically, the equipment will be handled by Kenneth Nguyen and Ramon Ponce. This task will be handled and obtaining all the necessary equipment to begin working on a product model that is not the prototype. AI training and modeling is under Ian Blankenship, Kenneth Nguyen, and Ramon Ponce. This task will involve taking information from the drone sensors and cameras and training an AI model to process this and make the best decisions so the drone stays autonomous, relying on the drone sensors to be functional and equipment to be handled. UAV simulations, Kenneth Nguyen and Ian Blankenship. Flight simulations for the drone. This will be to test the drone based on the parts and how it is being built. Drone construction will be Ethan Gable and Sebastian Valenzuela, relying on CAD designs to be complete. The construction of the drone, each part is to be individually and then systematically tested with the drone. CAD designs, Ethan Gable, Sebastian Valenzuela, designs for the drone and its many parts that go into it. Additionally, designs for a delivery mechanism and leaving space for this mechanism to go into the drone will be considered. Testing individual components, Ian Blankenship, Ethan Gable. Testing of the individual components, relying on the equipment to be bought. This will be conducted throughout the construction of the drone. Then checking integration of each system, Ethan Gable, Ramon Ponce, Sebastian Valenzuela. Making sure that the AI and the drone are secured and properly integrated with each other to ensure smooth autonomous flying. Run stability and control tests, Ethan Gable, Sebastian Valenzuela. Contrary to the simulations, these will be live tests conducted after simulations show no signs of any errors. This relies on drone construction to be majorly completed if not finished. Full system test will be under Ian Blankenship, Ethan Gable, Kenneth Nguyen, Ramon Ponce, Sebastian Valenzuela. Final product live testing, everything is deemed completed, and now it's time to fly the drone autonomously to check for any errors or inaccuracies and make changes accordingly. Finally, last adjustments and QA checks, Ian Blankenship, Ethan Gable, Kenneth Nguyen, Ramon Ponce, Sebastian Valenzuela. This is making sure that no changes or modifications need to be made to the drone and that everything is working properly as it should.